Okay, so the next thing we want to discuss, and this is going to be our last of the review of examples before we move on to more formal topics, is the translation group. Actually, there is another one after this. The translation group is pretty easy. So, so suppose that X is a point in Minkowski space. Right, so we represent X as X mu, right? Now, if I transform X mu to X mu prime, where what we do is that we add A mu as constant. So A mu is a set of 4 numbers taken from R4. So then we see that this is a 4-dimensional, this is a group, right? So this is called the translation group. Of the Minkowski space-time R13. So what does it do? It just changes, it just takes your Minkowski space, the spatial parts, it just moves it by some amount, either in the spatial directions or in the time direction or both. Okay? So, and this group is just R4, right? So the translation group is just R4, which is R cross R cross R cross R, right? Right? So this is each of which is an additive group. Okay, this should be pretty easy and clear, but if not, it's not. I mean, it's fine if it's not. So please ask me any questions.
So, I'm a bit confused that we are adding an element from a Euclidean space to an element in the Minkowski space. So that is a bit confusing to me. Is that possible, that addition?
Yeah, no. So what we mean by R13 is R4 with eta mu nu as the metric tensor, as the way to measure distance instead of delta mu nu. Okay, that's what we mean by Minkowski space. But the elements I'm adding to each of the coordinates in Minkowski space is just an element of R. Therefore, an element of this group is an element of R4. Or 4 factors of R4, R, right?
So is it like an element of R1,3 is being added with an element of R4, and then we get the new translated the coordinates?
Yeah, so T goes to T plus, say, T0, and say X goes to X plus X0.
So this is like if a point is on 2,2 and we add 2 on X, we get 4,2. So this is the simple thing, right?
Yeah, yeah. I mean, these guys are just, I mean, not these guys. What are the parameters here? The parameters are this. So we are adding this to all points of the Minkowski space. So we are taking the whole of Minkowski space and translating it, either in the spatial direction or the time direction or in both.
Oh,
right? Yeah, but the parameters, but the parameters are chosen from R4, right? I mean, the resultant T and X prime, T prime and X prime, we are still measuring the distance using the Minkowski metric.
So is this idea like this, that translation like this won't basically change our metric, so we're good to go with R1, 3 again?
Yeah, exactly. It's still taking us to R1,3. Yeah.
So I didn't get the R1,3 part, like R4 and R1.
So, like, I mean, when we are measuring, say, the interval, we are still using minus t squared plus x squared, right? And here, we are using the interval, which is t prime minus t prime squared plus x prime squared, right? So, this is mapping, this action is mapping a point in Minkowski space to another point in Minkowski space. Right, so let's take an example. Yeah, okay, good. So now we combine, so we know what the SO1,3 group is, the Lorenz group, and we know the translation group, and now we combine them into what is known as the Poincaré group. Okay, so the Poincare group is the group of symmetries of the Minkowski space. Okay, so it is a combination of the translation group R4 and the Lorenz group or orthochronous proper Lorenz group SO1,3, and there's a plus or something, right? Now, this is not a simple product. And to see this, let's take an element A from R4 and lambda from SO1,3. And call this element, A, like, let's take this ordered pair of these guys, right? Now, if I do two transformations, one after other, what is the result? So let's see. So the way we interpret the action of this is that, so this is the first set of transformation. First, we do a rotation. So we take a Minkowski space event. Well, we take all the events and we apply the lambda matrix, right? And then we do a translation on the result. So this is the resultant, which is lambda 1 mu nu. This is not, okay, yeah, I shouldn't say, why did I say rotation? I said, let's not call it rotation. Sorry, SO1,3. And then we translate it by an amount. Okay, so this is the first set, this guy. And then we do the second set of translation. So the first one is SO1, 3 transformation. Now we are making the transformation from this guy. So this is going to be lambda 2, and this is going to call this rho mu acting on lambda 1 mu nu x nu plus A1 mu, right? We are just, instead of this thing, we are inserting the result of the previous action. And then we do another translation. And that translation is, we take this whole thing, we add to it, A2. So let's write that out. So lambda 2 rho mu lambda 1 mu nu x nu plus A1 mu, and we add to it A2 of rho. Okay, so now we expand this. This is a Lorenz transformation acting on another Lorenz transformation, so we can call that is going to be another Lorenz transformation with rho nu acting on x of nu. Now this is a Lorenz transformation acting on a constant 4 vector. It's an element of R4, but it's a 4 vector nonetheless. So the action is quite well defined. So, so we have lambda 2 rho mu A mu. But this is plus A2 rho. But this guy plus this guy is a translation, right? Because it doesn't have an X dependence. So we can write this as lambda rho nu x nu plus A rho. So where A rho is defined to be this thing. Okay, so A rho is defined to be lambda 2 rho mu A1 mu plus A2 rho. So from this, we figure out that the multiplication rule for the Lorenz, for the Poincaré group is this. It is an almost direct product, but not quite. If this guy weren't there, then it would be a direct product, but it's not. So this is known as a semi-direct product. And it's written as R1, 3, O1, 3. Okay. This is also known as the inhomogeneous Lorenz group. Okay, so this is an important formula. All right, so this is, I think this is basically a good place for us to take a break, but let's have some questions first.
Sure. So you wrote this as R1, 3 and O3. So those lambda transformations, those are part of O3.
Yeah, it could have been, exactly. O1, 3.
O1, 3. So why not the special group here, sir? Like why not SO1, 3?
Oh, it could have been SO1, 3. Sorry, I misspoke. Yeah, sorry. It could have been, I realized that, sometimes, different people define these things differently, but I think to be completely rigorous, we should, thank you, Nahi. Yeah, these should be just O1, 3. Yeah.
And so what's inhomogeneous about this?
So, when we talk about linear transformations of this form, so this is a linear transformation, right? So this is what we would call, if I have, say, if I have a geometric, if I think of rotation, this is what we would call, a rotation like that, right? So these guys just rotate. They don't have any translation. But if you add a translation to it, then, you basically move away from the origin and you go somewhere else, right? And in terms of
won't work, that's why.
Sorry, I don't know. You can say it in that way as well. What do you mean superposition?
I mean, like adding to this kind of linear transformation probably won't breed another one, or is it something like that?
I mean, you're talking about essentially what you're saying is there's this structure, the semi-direct product. The way I wanted to form this is that, if I'm talking about matrices, this is a matrix operation, right? And we call these sort of operations homogeneous linear transformations. But if I add something, that's usually known as an inhomogeneous transformation. It's like, because this is somehow, it's just, when you have a wave equation, so this is your wave operator, this is called a homogeneous.
So when we have a source, we call it inhomogeneous, I guess.
Exactly. So here, because we have this term, this is quote unquote a source. Okay, any more questions before we go on a break? Okay, so let's take a break. All right, so welcome back. Are there any questions from what we've covered so far?
So could you explain the mu nu part one more time? Like I can't understand the notation yet, not clear fully.
You mean this one?
Yes, sir.
Okay, so lambda mu nu means that we have a matrix lambda and we are taking its row and column. So this is the row index and this is the column index. So when we write lambda mu nu acting on x nu, this means that I'm acting by a 4x4 matrix on a 4-dimensional column vector and taking its mu index. So this is a x prime, it's muth element. So if I were to expand this, this would be a 4x4 matrix acting on a column vector. How would I write it? I would write it as there's a sum over nu. So nu goes from 0 to 3, 0 being the time coordinate, and x of nu. So this is what the left-hand side is. But and the result is we get a nu. So this is just matrix multiplication, right?
The mu on the on top of x, does this mean there are new elements on
that
x?
Means there are 4 elements. So x, when we say x mu, we mean x0, x1, x2, x3. So mu takes the value of 0, 1, 2, 3.
Okay, got it.
And x0 is what we're calling time. We're using units where c is 1. If not, there would be a factor of C here, but we are not using that. And this x1 is x, y1 is, x2 is y, x3 is z, okay? But
Yes,
because we are using the Einstein summation convention, we don't write that explicitly. Okay, so
so this lambda mu nu, every time I see, I would compare it with a matrix.
It is a, it is a matrix. Yeah, it is a matrix element.
Got it.
It's not a matrix, it's a matrix element.